Hello everyone, am I audible? Hello everyone, am I audible? Am I audible? Please let me know if I'm audible. Okay, so here we are starting up with the reading of the chapter 1 force. Okay, I know students key it takes a big time to read, and by now you might have been already quite, what you can say, re-energized reading a lot, and so many of the students I have seen they get bored to read, but they're okay to hear, to listen, and this is the real reason why. On request of one of the viewer, we started off with this as well. So I'm starting up with the reading of the chapter Force, ICSE 10th standard. In class ninth, we have read that a force, when applied on a rigid body, can cause only the motion in it, while when applied on a non-rigid body, can cause both a change in its size or shape and the motion in it. In mathematical form, force applied on a body is defined as the rate of change in its linear momentum. That is, force is equal to dp upon dt is equal to d into brackets mv upon dt, or F is equal to ma if mass m is constant. The force is a vector quantity and its SI unit is Newton, symbol being N, or kilogram force. The symbol is kgf, where 1 kgf is equal to g capital N if g is the acceleration due to gravity, that is equal to 9.8 meter per second square on average. Now, let's start reading the first one, moment of a force and equilibrium. 1.1, translational and rotational motions. A rigid body, when acted upon by a force, can have two kinds of motion, linear or translational motion, and second, rotational motion. Linear or translational motion. When a force acts on a stationary, rigid body, which is free to move, the body starts moving in a straight path in the direction of the force. This is called the linear or translational motion. For example, in figure 1.1, on pushing a ball lying on the floor, it begins to move. Second is the rotational motion. If the body is pivoted at a point and the force is applied on the body at suitable point, it rotates the body about the axis passing through the pivoted point. This is the turning effect of the force, and the motion of the body is called as the rotational motion. For example, if a wheel is pivoted at its center and a force is applied tangentially on its rim as shown in the figure 1.2, the wheel rotates about its center. Similarly, when a force is applied normally on the handle of a door, the door begins to rotate about an axis passing through the hinges on which the door rests. Coming to 1.2, moment, turning effect of a force or torque. Consider a body which is pivoted at a point O. If a force is applied horizontally on the body with its line of action in the direction FP, as shown in figure 1.3, the force is unable to produce linear motion of the body in its direction because the body is not free to move, but this force turns or rotates the body about the vertical axis passing through the point O in the direction shown by the arrow in figure 1.3. That is, the force rotates the body anti-clockwise. Factors affecting the turning of a body. The turning effect on a body by a force depends on the following two factors. First, the magnitude of the force applied, and second, the distance of line of action of the force from the axis of rotation or pivoting point. Indeed, the turning effect on the body depends on the product of both the above stated factors. This product is called the moment of force or torque. Thus, the body rotates due to the moment of force or torque about the pivoted point. In other words, the turning effect on the body about an axis is due to the moment of force or torque applied on the body. Now, coming to the next, that is measurement of moment of force or torque. The moment of a force or torque is equal to the product of the magnitude of the force and the perpendicular distance of the line of action of force from the axis of rotation. In figure 1.3, the line of action of force F is shown by the dotted line FP and the perpendicular drawn from the pivoted point O on the line of action of force is OP. Therefore, the moment of force about the axis passing through the point O is equal to force into perpendicular distance of force from the point O, that is equal to F into OP. Note, for producing maximum turning effect on a body by a given force, the force is applied on the body at a point for which the perpendicular distance of line of action of the force from the axis of rotation is maximum, so that the given force may provide the maximum torque to turn the body. Now, coming to the next, units of moment of force. Unit of moment of force is equal to unit of force into unit of distance. The SI unit of force is Newton and that of distance is meter. So the SI unit of moment of force is Newton into meter. This is abbreviated as capital N small m. The CGS unit of moment of force is dynes into centimeter. But if force is measured in gravitational unit, then the unit of moment of force in the SI system is kgf into m, and in CGS system the unit is gf into centimeters. These units are related as follows. 1 Newton meter is equal to 10 raised to 5 dynes into 10 raised to 2 centimeters. That is equal to 10 raised to 7 dyne centimeter. 1 kgf into m is equal to 9.8 Newton meter, and 1 gf into centimeter is equal to 980 dyne centimeter. So friends, these relations are very important for you to solve the numerical problems that may appear in the exams. Also, this can be asked to you in any form. The relationship between different units can be certainly asked. You may be asked the SI unit, you may be asked the CGS system. Please keep this in mind. Now, coming to the next, clockwise and anti-clockwise moments. Conventionally, if the effect on the body is to turn it anti-clockwise, moment of force is called the anti-clockwise moment and it is taken positive. While if the effect on the body is to turn it clockwise, the moment of force is called the clockwise moment and it is taken negative. Remember, The unit Newton meter of moment of force or torque is not written as joule. However, the unit Newton meter for work or energy is written as joules, that is capital J, because torque is a vector while work or energy is a scalar quantity. This can be asked to you as assertion and reasoning type of questions, or it can be even asked to you as true or false. You find out the wrong statement, find out the right statement, and so on. Coming to the next, the moment of force is a vector quantity. The direction of anti-clockwise moment is along the axis of rotation outwards, while a clockwise moment is along the axis of rotation inwards. On applying the force on a pivoted body, its direction of rotation depends on, first, the point of application of the force, and second, the direction of the force. You can refer to figure 1.4a, which shows the anti-clockwise and clockwise moments produced in a disk pivoted at its center by changing the point of application of the force F from point A to point B. And in the figure 1.4b, it shows the anti-clockwise and clockwise moments produced on a pivoted axle by changing the direction of the force F and the free end of the axle. So you can zoom in and look at it closely. Very, very important. Even pictorial questions are asked. You can be shown such images, and image-based questions can be asked on this. Coming to the next, that is common examples of moment of force. To open or shut a door, we apply a force, that is push or pull. Capital F, that is force, normal to the door, and its handle P, which is provided at the maximum distance from the hinges as shown in the figure 1.5. I shall show you the figure. Here it is. So have a close look at it. The handle, the hinges, and the door. Okay. We can notice that if we apply the force at a point Q, that is near the hinge R, much greater force is required to open the door. And if the force is applied at the hinge R, we will not be able to open the door, howsoever large the force may be. Because of the force at R, torque will be zero. Thus, the handle P is provided near the free end of the door, so that a smaller force at a larger perpendicular distance produces the moment of force required to open or shut the door. So, look at this figure again. Coming to the next, that is point number 2. The upper circular stone of a hand floor grinder is provided with a handle near its rim, that is, at the maximum distance from the center, so that it can be easily rotated about the iron pivot at its center by applying a small force at the handle. For example, for turning a steering wheel, a force is applied tangentially on the rim of the wheel. You can see figure 1.6. The sense of rotation of the wheel is changed by changing the point of application of force without changing the direction of the force. In figure 1.6a, when force F is applied at the point A of the wheel rotates anti-clockwise, while in figure 1.6b, the wheel rotates clockwise when the force F is in the same direction as applied at the point B of the wheel. You can certainly relate this up when you see your parents driving the car when they take the wheel. So definitely observe this. Coming to the fourth example, in a bicycle, you turn the wheel anti-clockwise. A small force is applied on the foot pedal of a toothed wheel of size bigger than the rear wheel, so that the perpendicular distance of The point of application of force from the axle of wheel is large. This is a figure 1.7. You can look at it again. The two wheels are joined by a chain through their tooth. Right? Coming to the fifth example. Hi Preetham, pyari evening. Hi Abhinav, good evening bacha. How are you? Now coming to the fifth example. A spanner used to tighten or loosen a nut has a long handle to produce a large moment of force by a small force applied normally at the end of its handle as shown in the figure 1.8. The spanner is turned anti-clockwise to loosen the nut by applying the force in the direction shown in the figure 1.8, while it is turned clockwise to tighten the nut by applying the force in a direction opposite to that shown in the figure 1.8. You can have a close look at the figure so that you can relate it. Now, coming to the conclusion part from the examples that we read right now. From the above examples, we conclude that the turning of a body about an axis depends not only on the magnitude of the force, but it also depends on the perpendicular distance of the line of action of the applied force from the axis of rotation. Larger the perpendicular distance, less is the force needed to turn the body. Coming to the next 1.3 couple. A single force applied on a pivoted body alone does not cause rotation of the body. This, I can ask you whether this statement is a correct statement or a wrong statement. So listen to each and every statement carefully. A single force applied on a pivoted body alone does not cause rotation of the body. Actually, the rotation is always produced by a pair of forces. In the above examples, the rotation is due to the force externally applied and the force of reaction produced at the pivoted point. The force of reaction at the pivot is equal in magnitude but opposite in direction to the applied force. The moment of the force of reaction about the pivot is zero because its distance from the axis of rotation is zero. So the force of reaction at the fixed point or pivot is not shown in figure 1.3 to figure 1.8. Such a pair of forces is called as couple. Thus, two equal and opposite parallel forces not acting along the same line form a couple. A couple is always needed to produce a rotation. For example, when we open a door, the rotation of the door is produced by a couple consisting of two forces. First, the force which we exert at the handle of the door, and second, an equal and opposite force of reaction at the hinge. In case if we require a larger turning effect, the two forces equal in magnitude and opposite in directions are applied on the body explicitly such that both the forces turn the body in the same direction. Example, to open the nut of a car wheel, we apply equal forces. Each F at the two ends of the wrench are in opposite directions as shown in the figure. So the car wrench is being shown in figure 1.9a and the figure B shows the types of the movement brought about while opening the nut of the car wheel by a wrench. Similarly, turning a water tap, a very common example I can say. Figure 1.10. Tightening the cap of an ink pot, figure 1.11. Turning the key in the hole of a lock, figure 1.12. Winding a clock or a watch with the key, turning the steering of a motor car, figure 1.13. Driving the pedal of a bicycle, etc. are the other examples where a pair of forces that is coupled is applied for rotation. So please remember, two equal and opposite parallel forces not acting along the same line form a couple. आपको याद रखने के लिए आसान सी बात बता सकती हूँ. Your parents form a couple. Whenever, let's say, take an example, the school is organizing a picnic, overnight picnic. Okay, your mother says yes, you may go, and your father says no, you won't. Yeah, either or. So they both are talking about you. You are the common factor, but one is positive, one is negative. That is, they are equal, but they are opposite in direction. So you can remember this as an example that two equal and opposite parallel forces not acting along the same line form a couple. Coming to the next point, moment of couple. Figure 1.14 illustrates the action of a couple. AB is a bar which is 5 water at the point O. At the ends A and B, two equal and opposite forces, each of magnitude F, are applied. The perpendicular distance between the two forces AB is equal to D, which is called the couple arc. The two forces cannot produce a translational motion as their resultant sum in any direction is zero, but each force has a turning effect on the bar in the same direction. Thus, the two forces together form a couple which rotates the bar about the point O. In figure 1.14, the two forces rotate the bar in anti-clockwise direction. So look at this particular diagram properly. Now, moment of force F at the end A is equal to F into OA, that is anti-clockwise. Moment of force F at the end B is equal to F into OB, that is also anti-clockwise. So total moment of the couple, that is moment of both the forces, is equal to F into OA plus F into OB, that is equal to F into brackets OA plus OB, that is F into AB, that is F into D, that is anti-clockwise. So the moment of the couple is equal to either force into perpendicular distance between the two forces or couple arc. Very, very important relation. In other words, the moment of couple is equal to the product of the either force and the perpendicular distance between the line of action of both the forces. Now coming to the next, that is 1.4, equilibrium of the bodies. We have read that when a force acts on a body, it can produce translational motion if the body is free to move, or can produce rotational motion if the body is fixed at a point. But it is possible to apply a number of forces, two or more, such that first the resultant of all forces is zero, so they do not change the state of rest or motion of the body, and second, the algebraic sum of moments of all forces about the fixed point is zero, so they do not change the rotational state of the body. Then the body is said to be in the equilibrium. Thus, when a number of forces acting on a body produce no change in its state of rest or of linear or rotational motion, the body is said to be in equilibrium. Very, very, very important. I repeat this point so that you should remember, when a number of forces acting on a body produce no change in its state of rest or of linear or rotational motion, the body is said to be in equilibrium. Now, coming to the next, that is kinds of equilibrium. The equilibrium is of two kinds. First, static equilibrium, and second, dynamic equilibrium. Let's understand first that the static equilibrium. When a body remains in the state of rest under the influence of several forces, the body is in static equilibrium. Examples. First, In figure 1.15, if a body lying on the tabletop is pulled by a force F to its left and by an equal force F to its right along the same line, the body does not move. The reason is that the applied forces are equal and opposite along the same line, so they balance each other. That is, there is no net horizontal force on the body. Hence, the body remains at rest, that is, in static equilibrium. Now, this is quite easier for anybody to understand. Imagine you're standing at the center and two friends of yours who are exerting equal force on you are pulling you in opposite directions by both of your hands. In that case, you will be remaining stable. Neither you move towards the right nor you move towards the left. In simple words, you are in a state of rest, that is static equilibrium. Coming to the second, if a ball is lying on a table, if a book is lying on a table, the weight of the book exerted on the table vertically downwards is balanced by the equal and opposite force of reaction exerted by the table on the book vertically upwards. Thus, the book is in static equilibrium. Coming to the third, in a beam balance, when the beam is balanced in horizontal position, the clockwise moment of force due to object on its right pan balances the anti-clockwise moment of force due to weights on its left pan, and the beam has no rotational motion. That is, it is in the static equilibrium. Second, let us understand about dynamic equilibrium. When a body remains in the same state of motion, that is translational or rotational, under the influence of the several forces, the body is said to be in dynamic equilibrium. Examples. First, a raindrop reaches the earth's surface. A raindrop reaches the earth's surface with a constant velocity. Drop is zero, so it moves with a constant velocity. This could be asked: raindrop move with a constant velocity. Yeah, why? Why the force on the drop is zero. Coming to the second example, an aeroplane moves at a constant height when upward lift on it balances its weight downwards. Third, a stone tied at the end of a string, when whirled in a circular path with a uniform speed, is in dynamic equilibrium because the tension in the string provides the centripetal force required for circular motion. Similarly, the motion of a planet around the sun, or the motion of a satellite around the planet, or the motion. Now, suspend two spring balances, A and B, on the meter rule with some slotted weights as W1 balance, or the position of the spring balance on either side of the thread in such a way that the meter rule again becomes horizontal. Let the weight suspended on the right side of the thread from the spring balance A be W1 at a distance OA is equal to L1, while the weight suspended on the left side of the thread from the spring balance B be W2 at a distance OB, that is L2. Prashant Savalgi, definitely we will be uploading one more paper, don't worry. We have 4 papers to solve for physics. Very soon after this video, after this, what we are doing the reading session so that you all can have a quick, what you can say, revision of the entire textbook, even while you're on the way to the schools. That's the real reason why this particular session is being done. Okay, but certainly, Prashant, आपके लिए definitely we will be uploading another physics paper, so you please stay tuned. If you're new to the channel, kindly subscribe to our channel and hit the bell icon so that you get to know as soon as we come for the next live stream session. Now, the weight W1 tends to turn the meter rule clockwise, while the weight W2 tends to turn the meter rule anti-clockwise. Clockwise moment of weight W1 about the point O is equal to W1 into L1, and anti-clockwise moment of the weight W2 about the point O is equal to W2 into L2. In equilibrium, where the meter rule is horizontal, it is found that W1 L1 is equal to W2 L2. That is, clockwise moment is equal to anti-clockwise moment. This verifies the principle of moments. Now, these are the examples that have been given. So, I shall read that as well. The numerical reads, first, a body is pivoted at a point A. It's pivoted at a point. A force of 10 newtons is applied at a distance of 30 centimeter from the pivot. Calculate the moment of the force above the pivot. So you first always, while solving these numericals, always write what is given, the data you find what is given. So given is F is equal to 10 newtons, small r is equal to 30 centimeters, that is equal to 0.3 meters. So while calculating the moment of force, that is calculated by the formula F into R is equal to 10 into 0.3, that is 3 Newton meter. Coming to the second example, the moment of a force of 5 newtons about a point P is 2 Newton meter. Calculate the distance of point of application of the force from the point P. So given is moment of force is equal to 2 Newton meter and force is equal to 5 newtons. If the distance of the point of application of force from the point P is r meters, then moment of force is equal to force into distance, or 2 is equal to 5 into r. Therefore, r is equal to 2 by 5, that is 0.4 meters. Now, coming to the next, a mechanic can open a nut by applying a force of 150 newtons while using a lever handle of length 40 centimeters. How long handle is required if he wants to open it by applying a force of only 50 newtons? In the first case, F is equal to 150 newtons, R is equal to 40 centimeters, that is equal to 0.4 meters. So the moment of force needed to open the nut will be equal to 150 newtons into 0.4 meters, that is equal to 60 Newton meters. In the second case, force is equal to 50 newtons. So if he uses the handle of length L, M, then moment of force is equal to 50 newtons into Lm, that is equal to 50 Lnm. That is, from equations you get to know 50 L is equal to 60, or L is equal to 60 by 50, that is equal to 1.2 meters. Now friends, I think this exercise can be skipped because it makes no sense. You'll have to actually write and solve it. So I go ahead. So I hope you have already solved it. Let's go to the second part, that is center of gravity. 1.6, we're talking about the center of gravity. We have read in class 9th that the gravitational force is always attractive. So, the earth attracts every particle towards its center by the force of gravity on the particle, that is equal to weight W. A body can be considered to be made up of a large number of particles of weight W, W2, W3, etc. As the size of the body is quite small in comparison to the size of the Earth, the force of gravity W acting on these particles can be assumed to be parallel to each other as shown in the figure 1.35. All these parallel forces acting in the same direction, that is, vertically downwards towards the center of the earth, can be replaced by a single resultant force of magnitude equal to the sum of all these forces, that is equal to the entire weight, that is capital W, which is equal to W1 plus W2 plus W3 plus so on of the body. Now the question arises, where should this weight W act? And the weight capital W is considered to act at the point G such that the algebraic sum of moments due to weights W1, W2, etc. of each particle about the point G is 0. The point G is called the center of gravity of the body. In other words, the body can be considered as a point particle of weight capital W placed at its center of gravity G. Thus, the center of gravity, that is CG, of a body is the point about which the algebraic sum of moments of weights of all the particles constituting the body is 0. The entire weight of the body can be considered to act at this point, howsoever the body is placed. Note, first, the position of the center of gravity of a body of given mass depends on its shape, that is, on the distribution of mass of particles in it. It changes if the body is deformed. Example, the center of gravity of a uniform wire is at the middle of its length. But if the same wire is bent into the form of a circle, its center of gravity will then be at the center of the circle. Second, it is not necessary that the center of the gravity always be within the material of the body. Example, the center of gravity of a ring or a hollow sphere lies at its center where there is no material. By the concept of center of gravity, a body of weight capital W can be considered as a point particle of weight capital W at its center of gravity. So here's now I'm reading up the center of gravity of some regular objects. So the first one is object, that is rod, and the center of gravity for the rod will be the midpoint of the rod as shown in the figure 1.36. Here it is. Okay. Second one, circular disc. The center of gravity is the geometric center. Once again, you can look at the figure so that you get to know the circular disc. That is this one. If you can look at the pointer that I'm pointing at. Third one, solid or hollow sphere. The center of gravity will be the geometric center of the sphere. Fourth, solid or hollow cylinder. The center of gravity is the midpoint on the axis of the cylinder. Fifth, solid cone. The center of gravity will be at a height h by 4 from the base on its axis, wherein h is equal to the height of the cone. Sorry. Sixth, hollow cone. The center of gravity is at a height h by 3 from the base on its axis, where h is equal to height of the cone. Seventh, circular ring. The center of gravity is the center of the ring. Eighth, triangular lamina or scalene triangle. The center of gravity is the point of intersection of the medians. Ninth, parallelogram, rectangular lamina, square or rhombus. The center of gravity is the point of intersection of the diagonals. Figure 1.36 shows the position of center of gravity by the point capital G for a circular ring, a circular disc, a triangular lamina, a rectangle, a parallelogram, a square lamina, a rod, and a cylinder. Please have a close look at the diagrams given. Now, Coming to the next, that is center of gravity and the balance point. A solid body can be balanced by supporting it at its center of gravity. For example, a uniform meter rule has its center of gravity at the mark 50 centimeter. It can be balanced on a knife edge or fingertip by keeping it exactly below the 50 centimeter mark as shown in the figure 1.37. It is possible because the algebraic sum of moments of the weight of all the particles of the rule about the knife edge or fingertip is 0. Yes, Prem Sahu, definitely we will try for reading out all the chapters. Okay, definitely if this is the request you have to make, definitely I will take up your request. But only thing you will have to hang on. Okay, even if it's midnight, I shall be there with you. Okay, we also have 2 3 papers to solve in between. We shall schedule it like that. Okay, but definitely if this is helping all the children, I am more than happy to help you out in this way so that even on the way to the school you can keep listening and keep revising. So बच्चा definitely आपके लिए ये करूंगी. आपसे सिर्फ इतनी रिक्वेस्ट है, can you please ask your other friends also to join in so that even they will be benefited. I continue. Similarly, a square thin sheet or lamina can be balanced on the tip of a nail as shown in the figure 1.38. So figure 1.38, have a close look at it. A square sheet balanced on the tip of a nail. If a body is freely suspended from a point, it comes to rest, that is, balances, in such a position that its center of gravity lies vertically below the point of suspension. This fact can be used to locate the position of center of gravity of an irregular lamina. Now, coming to the next, determination of center of gravity of an irregular lamina by the method of balance using a Plumb line. Let capital A be an irregular lamina in the figure 1.39 for which the position of center of gravity is to be determined. Make 3 fine holes at A, B and C near the edge of the lamina. Now suspend the given lamina along with the Plumb line from the hole A using a pin or a nail clamped horizontally on a retort stand. Check that the lamina is free to oscillate on the nail about the point of suspension. When lamina has come to rest, draw a straight line AD along the Plumb line. Repeat the procedure by suspending the lamina through the hole B and then through the hole C, for which we get straight lines BE and CF respectively. It is noticed that the lines AD, BE and CF intersect each other at a common point G, which is the position of center of gravity of the lamina. Now again, you have the exercise questions. I hope you have already solved them. We come to the third part, that is the uniform circular motion. Now, 1.7 uniform circular motion. When a particle moves with a constant speed in a circular path, its motion is said to be the uniform circular motion. In such a motion, the particle travels equal distance along the circular path in equal intervals of time, so the speed of the particle is uniform, but the direction of motion of the particle changes at each point of circular path. The continuous change in direction of motion implies that the velocity of particle is non-uniform or variable, that is, the motion is accelerated. Direction of velocity at any instant in a circular path. Figure 1.42 shows a particle moving in a circular path in a horizontal plane with uniform speed v in the anti-clockwise direction. The particle travels each quarter of the circle AB, BC, CD, and DA in the same interval of time. That is, small t is equal to capital T by 4, where capital T is the time taken by the particle in one round of the circular path. Thus, the speed of particle is constant or uniform, but the direction of motion of the particle is different at different points of the circular path. At any point, the direction of motion is along the tangent drawn at that point of the circular path. Very, very important point. At the point A, the direction of motion of the particle is towards north. After completing quarter of circle at the point B, the direction of motion of particle is towards west. After completing half circle at the point C, the direction of motion of particle is towards south. And after completing 3/4 of the circle, when the particle is at the point D, its direction of motion is towards east. Thus, the velocity of the particle in circular motion is variable, or the circular motion is accelerated even though the speed of particle is uniform. Coming to the next, that is difference between the uniform circular motion and uniform linear motion. In uniform circular motion, the speed and velocity are constant and acceleration is zero. That is, the uniform linear motion is an unaccelerated motion, while in a uniform circular motion, the velocity is variable, although the speed is uniform. So it is an accelerated motion. Coming to the next, that is 1.8, we ought to talk about centripetal and centrifugal force. Centripetal force. We have read that in the linear motion, a force is needed to change the direction of motion of a particle or to change the velocity of the particle, that is, to produce acceleration. In circular motion, at each point of the circular path, the particle continuously changes its direction of motion. This change in direction of motion cannot be brought without a force. Thus, the motion in circular path is possible only under the influence of a force which is termed as centripetal force. At each point of circular path, this force is directed towards the center of the circle, as shown in the figure 1.43. Thus, the direction of acceleration also changes at each point of the circular path, but its magnitude remains the same. That is, the acceleration is variable or non-uniform. Hence, for a body moving in a circular path, a force is needed which acts as a centripetal force. So you can have a close look at this particular image. Now please remember the word centripetal means center seeking, that is, which goes towards the center from the periphery. Now coming to the examples. First example, in an atom, an electron moves around the nucleus in a circular path for which the centripetal force is obtained from the electrostatic force of attraction on the negatively charged electrons by the positively charged nucleus. Example number 2. A planet moves around the sun in a circular path for which the gravitational force of attraction on the planet by the sun provides the necessary centripetal force. Third example, the moon moves around the earth in a circular path for which the gravitational force of attraction on the moon by the earth provides the centripetal force. Fourth, when a stone tied at the end of a string is whirled in a circular path, the tension in the string holding the stone at the other end provides the centripetal force. If this force is not present, the stone will not turn to move in the circular path. In all the above examples, the body moves in circular path with a uniform speed under the influence of a centripetal force, and it is in dynamic equilibrium. Now, We come to the next, that is centrifugal force. A force acting on a body away from its center of circular path is called the centrifugal force. Thus, centrifugal force is in a direction opposite to the direction of centripetal force. Its magnitude is same as that of the centripetal force. But centrifugal force is not the force of reaction of the centripetal force because action and reaction do not act on the same body. It is not the real force, but is a fictitious force assumed by an observer moving in circular path along with the body. To understand this force, consider the following experiment. So we come to the experiment, the figure 1.44. You can see this shows a ball tied at one end of a string and the other end of which is tied at the center of a merry-go-round. Initially, when the platform of merry-go-round is stationary, the ball is seen stationary and the string is loose. As the platform starts rotating, the string becomes tight due to the tension capital T in it. The motion of the ball is observed by two persons. First, standing outside the merry-go-round on the ground at capital M, and second, standing on the platform of the merry-go-round at point capital A. The person standing at capital M outside the merry-go-round on the ground observes that the ball is moving in a circular path shown by the dotted line, while the person standing on the merry-go-round at capital A observes that the ball is stationary, placed just in front of him at capital B. As the merry-go-round rotates, the position of the person on the platform changes from A to A dash, A double dash, A triple dash, and so on, and the ball reaches at the position P dash, P double dash, P triple dash, and so on respectively, as if it remains at rest, always just in front of it. The different observations of the same motion by the two persons at capital M and capital A are explained as follows. Here starts the explanation. For the person at capital M, the ball moves in a circular path because the tension capital T in the string provides the centripetal force needed for the circular motion. The person at capital A observes the ball stationary. He considers following two forces to understand his observation. First, the tension capital T in the string towards the center of the merry-go-round, and second, the centrifugal force on the string away from the center. The above two forces are equal and opposite. Therefore, the net force on the ball is zero. Hence, it always remains stationary in front of him. Thus, a person on the rotating platform can explain his observation only by considering the centrifugal force. Now, consider the case. If the string breaks when the ball is in position capital P, as shown in the figure 1.45, the force of the tension capital T in the string ceases to act. Now, the person at capital M standing on the ground will observe that the ball is moving in a straight line along the path capital P capital D, which is the tangent drawn at the point P on the circular path, while the person standing on the merry-go-round will observe the ball at the positions P dash, P double dash, P triple dash, and so on, when he will be at positions A dash, A double dash, A triple dash, respectively. That is, he will observe that the ball always remains in front of him, moving radially away from him, as if a centrifugal force acts on the ball away from the center. Thus, the person in the rotating frame, that is merry-go-round, has to assume the presence of the centrifugal force. So you can look at this image close. You can zoom in and see this. Now, coming to the conclusion part of it, the centrifugal force is not a real force, It is a fictitious force. The only force involved here is the force of tension in the string acting towards the center, that is the centripetal force. So please remember, centrifugal force is a fictitious force. A force which really does not exist but is considered to describe or understand a certain motion is called as a fictitious force or virtual force. Please keep this in mind. It's very important. So with this, we have completed the reading part of the first chapter, that is force. In few minutes, we shall catch up soon. So kindly hang on to this channel. Okay, if you're new, please subscribe, and whatever you need from us, whatever is your demand, kindly suggest us about the same in the comment section after the video gets over. Okay, if you have really liked in the efforts that we are trying to put in for you all, definitely we deserve a like button if you feel so. Okay, and please hit the bell icon as well so that you get to know as soon as we come live stream.